Welcome to EPG Pathshala. In this module, we shall discuss methods for grouped and ungrouped binary data. We have discussed some methods for binary data, including logistic regression and calculating summaries from 2x2 and other contingency tables. Here we shall look at two kinds of binary data. In the first case, we shall look at grouped data. Grouped data arises when the binary outcomes are clustered according to the levels of some categorical covariate. It could also arise when the covariate is continuous. So say for example, we have performed a controlled experiment and our covariate is temperature, then we could fix the temperature at certain pre-specified levels and take more than one observation binary outcome at each level of temperature. So first we shall concentrate on methods for group data and see that it is common to employ methods and extensions of ordinary least squares. Next we shall move on to ungrouped data. Ungrouped data arises when we have a binary outcome and the outcomes correspond to covariates which can be categorical or continuous, that is mixed covariates, and we do not have more than one observation corresponding to each covariate. So this will typically arise in the case of a continuous covariate. So say for example, our covariate is age and we are looking at whether or not a person has lung cancer. In that case, for each value of age, as age is continuous, we would not expect to get more than one observation. So here all the OLS methods will break down. However, we still can recourse to maximum likelihood. So in this module, we will concentrate on OLS for group data and maximum likelihood methods for ungrouped data. Of course, the maximum likelihood methods can also be applied to group data. Finally, we shall look at some measures of goodness of fit, notably the deviance, and see that there are some issues with the performance of these criterion in the case of ungrouped data. Learning objectives for this module. First, we shall introduce the setting of grouped binary data. Next, we shall introduce the simplest model for this setting, which is the linear probability model. We will next move on to extensions, notably the Logit and the Probit in the case of group data, though of course there may be other links, and we shall motivate this using a binary choice approach. Finally, we shall move on to ungrouped data and see that all the methods we have mentioned before will break down and we will need to use maximum likelihood for the purpose of inference. Grouped and ungrouped binary data. Now we know that when we are in a regression setting, our focus is either to predict an outcome y in terms of several explanatory variables, x1, x2, x3 and so on, or to study how y depends on this set of covariates. So here for example is a typical regression equation which relates the savings of a country to the number of population under 15, the population over 75, etc. Now there can be many types of outcomes and some of them are listed here. So household income, family size, whether or not employed, share prices, whether or not studying for higher degree, mortality, morbidity, fertility, and so on. From the perspective of a statistician, these variables are classified depending on whether they are continuous or discrete, and if discrete, whether or not they can be binary, counts, and other rates, and so on. For this module, we shall concentrate on variables such as whether or not employed, which is a binary variable, and we shall see how we can adapt regression fitting to the case when the outcome is binary. We have mentioned before binary choice models. So, for example, suppose that our outcome is whether or not an individual migrates to a different country, yes or no, and we wish to determine what characteristics decide this. Or alternatively, suppose we are interested in an outcome such as whether or not a person is employed or not employed, and we wish to see what predictors will give a good estimate of labor force participation. The simplest model in this setting is the linear probability model. As the name suggests, we specify expectation of y given x and beta, where beta is the unknown vector of regression coefficients, is equal to x prime beta. We know that for a binary outcome, expectation of y given x beta is equal to the probability of y equal to 1 given x, and hence the linear probability model specifies probability of y equal to 1 given x equal to x beta. Here is an application to a school choice data example. So here we are looking at the probability of an individual opting for private school, and this has been plotted as a function of the linear predictor. As the model suggests, the regression line is a straight line relating probability to the linear predictor. However, the linear probability model has some shortcomings. Firstly, we can get predictions which are either less than 0 or greater than 1. In the school choice example, there are 61 observations for which the predicted probability is larger than 1 and 81 observations for which the predicted probability is less than 0. Other shortcomings: firstly, it does not make sense to say that a probability is linearly related to a continuous independent variable for all values of the variable, because this would imply that if we can continuously increase this continuous variable or perhaps decrease the continuous variable without limit, we would ultimately force the probability to lie either above 1 or below 0, which we know is not acceptable. So, for example, the model fitted to the school choice predicts that an increase in parental wealth by 1 unit will increase the probability of going to a private school by 1 percentage point. Now, at the extremes of income, that is in either very rich or very poor families, the wealth effect is probably smaller. In fact, the model specifies that a 100-fold increase in wealth will increase the probability of going to a private school by more than 1, which we know is not an acceptable answer. Another shortcoming of the linear probability model is that the residual is heteroscedastic by definition. This arises from the fact that if we calculate the variance of u given x, then direct calculation shows that this is given by x beta into 1 minus x beta, and since the values of the covariate x are different for each individual, this implies that the residuals are heteroscedastic. We know that the usual regression assumptions required for the validity of the Gauss-Markov setup are that expectation of y given x1, x2, etc. is x prime beta, and variance of y given x1, x2, x3 is sigma square, the y's being independently distributed. Applying the linear probability model to the binary setting leads to heteroscedastic errors. This means that OLS estimator is still unbiased, but the conventional formula for estimating the standard errors and t-values, and also hence the p-values, will all be incorrect. Let us next move on to two alternatives which are more commonly used when we have binary data, which is the Logit and the Probit model. So consider a class of general binary response models. The models specify the probability of y equal to 1 given x is equal to some function capital G of x beta, where g is chosen so that it lies between 0 and 1. This model is referred to as an index model because y depends on the vector x only through the index x beta. The choice of g is open to the user. It is usually chosen to be a cumulative density function which is monotonically increasing. This guarantees that probability of y equal to 1 given x will tend to 1 as x beta tends to infinity and tend to 0 as x beta tends to minus infinity. The Logit model arises when we use a logistic CDF. So in this case, g of x beta is equal to e to the power x prime beta by 1 plus e to the power x prime beta. This is a plot of the logistic regression model. As you can see, it gets around the assumption of linearity. It is S-shaped and lies between the values of 0 and 1. Another alternative is the Probit model, which specifies that g of x beta is the standard cumulative normal density. In this case, we see the plot corresponding to the Probit model. This is quite similar to the logistic model except in the tails, and here too we see an S-shaped curve lying between the values of 0 and 1. The key specification for the Logit and Probit models is thus probability of y equal to 1 given x equal to g of x beta, where g is some CDF. To get a justification, let us turn to a latent variable framework. Now, in econometrics, Probit and Logit models are traditionally viewed as models which are suitable when the dependent variable is not fully observed. So, for example, let y star be a continuous variable that we do not observe, and let us assume that y star is equal to x beta plus e. The variable we observe is y, and this is related to y star by the relationship that y is equal to 1 if y star is positive and y is equal to 0 if y star is less than equal to 0. So y here is unobserved, and it represents the net utility of the action of y equal to 1. So say for example the event y equal to 1 denotes buying a car. In that case, an individual will buy a car depending upon whether the net utility of buying the car is positive, and this utility will be a function of his observed covariates in the form of the linear predictor x beta and some random error. If we assume that this random error e follows a logistic distribution with density function lambda e equal to e to the power minus e by 1 plus e to the power minus e whole squared, we can show that this leads to the logistic model. So note that probability of y equal to 1 given x is the probability of y star positive, which by definition of y star is the probability of x beta plus e being greater than 0, which is the probability of e being greater than minus x beta. We assume that E has a symmetric distribution as it is a random error, and this leads to the derivation of probability of y equal to 1 given x is lambda of x beta, where lambda represents the CDF. For the Probit model, the same calculations would hold, and here it is possible to show that probability y equal to 1 given x is equal to capital phi of x beta, where capital phi denotes the CDF of the standard normal distribution. The same conclusions hold for the Probit model. For the Probit model, it is possible to show that probability y equal to 1 given x is equal to capital phi of x beta, where capital phi represents the CDF of the standard normal distribution. Grouped data. Now note that if we want to fit a logistic regression model to the case where we have grouped data, first observe that in case of grouped data for each covariate value x, we are able to find the corresponding proportions of success as we have more than one individuals at each covariate value. Then assuming the linear probability model pi equal to pi I plus ui, we define zi equal to phi inverse of pi, which is phi inverse of pi I plus ui star, and by a Taylor series expansion, it is possible to show that the implication is that zi is equal to xi prime beta plus vi. So this is in the form of a linear model where the variance of Vi is given by pi I into 1 minus pi I by Ni into phi square xi prime beta. Thus, to fit this Probit model to the group data, it is possible to perform estimation via GLS, and the form of beta hat is given by beta hat equal to x prime omega inverse x whole inverse by x prime omega inverse p, where p is the vector of pi's. Omega is diagonal pi I 1 minus pi I by Ni phi square xi prime beta, and note that as the pi i's are unknown, we can substitute them by the pi's. The same thing can be done when we wish to fit a logistic regression. So here too we apply the same Taylor series expansion, and in this case we get a GLS with the residual variances being 1 over Ni pi into 1 minus pi I. However, note that when we move on to ungrouped data, the observed proportions will either be zeros or ones, and so our previous method breaks down completely. We can no longer use the transformations in the raw data. So for example, log of 0 is not defined. We can also not use exploratory plots because they will tend to cluster around the values of 0 and 1 and be difficult to interpret. However, note that the parameter interpretation remains the same. So if pi x is equal to the probability of y equal to 1 given x, the logistic model would specify pi x equal to e to the power alpha plus beta x by 1 plus e to the power alpha plus beta x, or equivalently logit of pi x is equal to alpha plus beta x. Beta continues to represent the log odds ratio irrespective of whether we have grouped data or ungrouped data. However, the inference procedure will now change. Note that although it is not possible to perform least squares, it is possible to apply the principle of maximum likelihood estimation, and that the likelihood of beta is given by the expression given on this slide. Once we can write down the likelihood, it is possible to find the score equations. Note that numerical techniques will be required to maximize the likelihood. We can obtain standard errors from the inverse information matrix and construct hypothesis tests based on Walls test, score test, or the likelihood ratio test. The score equations are obtained by using the chain rule and taking the derivative of L beta with respect to beta, and this slide gives the score equations for the case where we have a logistic regression model. It is also possible to find the information matrix. Note that the Logit model represents a canonical link, and hence the information matrix will not involve y. It is also possible to find the information matrix for the Probit or any other link using the formula given here, although in this case the function will depend on y. The last line given on this slide represents the IRLS equations for estimating beta. The interpretation of logistic regression continues to be the same. So for example, if we have a single continuous explanatory variable x, and we are looking at the odds of PUA, which represents participation in a private school, given a covariate S raven, then we can write down the equations for x and x plus 1, and taking the difference, we can see that this leads to the result that e to the power beta 1 is the odds ratio, comparing the case S raven equal to x plus 1 to the case where S raven is equal to x. A utility of multiple logistic regression is that it is easy to incorporate multiple covariates, and we see here a logistic regression model for the outcome PUA in terms of two covariates, male, which is a binary covariate, and S raven, which is a continuous covariate. Checking the appropriateness of the link empirically might be difficult. The suggested procedure from Agresti is to use plots of log of yi plus half by ni minus yi plus half. Alternatively, we can use justification such as the latent variable framework, which I have discussed before. The plots could be unsatisfactory for ungrouped data. One alternative could be smoothing, and this has been illustrated in the book by Agresti. Inference for the logistic regression. Once we have defined the maximum likelihood procedure, as I said, it is possible to use likelihood-based methods such as Walls test, likelihood ratio test, score test. These can be inverted to get confidence intervals, And finally, we can use the deviance as a measure of goodness of fit. The deviance, as you know, is defined as minus twice log of the maximum likelihood for the model divided by the maximum likelihood for the saturated or the best fitting model, the best fitting model being that model which will return y as the predictor of y. On this slide, we see the deviance for the binomial model, and it is possible to show by exploring this formula further that in the case where the ni's are all equal to 1, that is, we have ungrouped data, it turns out that the deviance is a function of the odds ratio, which is an undesirable situation. This is defined as the sparsity problem for ungrouped data. In this module, we have looked at methods for grouped and ungrouped binary data. Grouped binary data arises when we have an outcome and we have multiple values corresponding to the same value of the covariate. This would arise, for example, if we have a categorical covariate. We have seen that the first model of choice for ungrouped binary data is the linear probability model, which can be fitted using least squares. However, it has some undesirable properties, and hence we have next used the binary choice framework to arrive at the logistic and the Probit model. We have used Taylor series expansions to derive the corresponding regression equations and have seen that these can be fitted using GLS. However, there are problems with this GLS fit as the residuals are heteroscedastic and also unknown. We plug in sample estimators of the unknown variances. Moving on to ungrouped data, all these methods will fail completely as it is no longer possible to calculate the corresponding sample proportions to each value of the covariate. These sample proportions. Moving on to ungrouped data, the previous set of methods would fail completely as it is no longer possible to calculate sample proportions corresponding to each value of the covariate. These proportions would take the value 0 or 1 as we would not have more than one observation for each covariate value. However, although it is not possible to apply the technique of least squares, we can use the principle of maximum likelihood. We have written down the likelihood, the score equation, the information matrix, and we know that it is possible to use tests like the Walls test, score test, and likelihood ratio test for the purpose of statistical inference. Of course, the technique of logistic regression can also be applied to the case where we have ungrouped data or grouped data, as the extra term in the likelihood from the grouping is a combinatorial term which does not involve the unknown parameters. Finally, we have looked at goodness of fit, specifically the deviance criterion, and we have seen that in case we have ungrouped data, the deviance function turns out to be a function of the odds ratio, which is undesirable. This is defined as the problem of sparseness for ungrouped binomial data, and we shall explore this further in a subsequent module. Thank you.